All right, this is an Algebra 2 video on solving exponential equations, and in particular we'll be solving them without using logarithms. I'll show you a couple different strategies to use if we're not going to use logarithms. We'll get to logarithms in a few days. And this will start off with an introduction and then do a couple examples. So by way of brief introduction, what we're trying to solve here are equations where there is an unknown in the exponent. Okay, so as an example, we won't solve this particular initial introductory example, but just as an example, if we have something like this, 5 to the 2x equals 18, we want to solve for x, get x by itself. Now there are a couple initial sort of instinctive strategies that students sometimes try to use. Sometimes students try to take maybe a square root of both sides, or maybe divide both sides by 5 in this case. If we're trying to get rid of that 2, maybe thinking about a square root of both sides, or if we're trying to deal with a 5, somehow dividing by 5. And neither of those strategies are particularly effective. We ultimately want a strategy that'll turn this somehow into x equals something. X equals our answer, right? And our ultimate strategy will be to use logarithms for that. But for now, I'll show you a couple strategies without the need for logarithms. So the first strategy is to get a common base. And I want to remind you, as we look over at our first example, 16 to the 3x equals 8, I want to remind you what the bases are. Okay, we have a base of 16 on the left, and on the right we have a base of 8. You might be curious, why is that called the base? Well, you could think of it as 8 to the 1, right? So you could think of it as an exponential expression, 8 to the 1. If we could get a common base, we'd be making some good progress here, but 16 and 8 are not equal. They're different values, right? So we need to try to turn them into equivalent values somehow. This is going to be a lot easier if you are familiar with some power sequences. Okay, so I'll write those over on the left-hand side. If we have powers of 2, 2 to the 0 is 1, 2 to the 1 is 2, 4, 8, 16, 32, 64, 128. You could keep going literally forever, okay? And then powers of 3, we could have 1, 3, multiplying by 3 each time, 27, 81, 243, and that's all I have memorized at this point, okay? But we're going to be looking for some common expressions, or some common values in those sequences. And hey, let's do powers of 4 as well, multiplying by 4 each time, 16, 64, 256. So that might just be some sequence of numbers to kind of have handy. I hope you're seeing that 16 and 8, even though 4 might come to mind initially, both of those numbers don't show up as powers of 4, but they do show up as powers of 2, okay? So let me just label this powers of 2, 3, and 4. Okay, so again, a table that I think would be handy to maybe have in your notes or kind of have on the top of your mind. Okay, so we can express each of these numbers, 16 and 8, as a power of 2. 16 is 2 to the 4th, and then that's all raised to the 3x, and 8 is 2 cubed. So I want to remind you of our rules for exponents, and when we have a base raised to a power, which is then raised to another power, we are allowed to multiply those powers together. So here's what this turns into. This turns into 2 to the 12x equals 2 to the 3. So we've reached our goal of developing a common base. 2 to the 12x equals 2 to the 3. And now I hope you can intuitively understand that 12x must equal 3. To get to this step, we're not dividing by 2. We're simply removing a 2 or making the realization that if we have equivalent bases raised to different powers and they're equal, those powers themselves must be equal. Okay, so 12x is equal to 3. A simple algebra 1 problem now, divide both sides by 12, and x equals 0.25. Okay, and you could actually go to your calculator and check this. you could do a quick check and just plug in x, and let's just plug it into the left side. what is 16 to the 3 times 0.25? So in other words, 16 to the 0.75, and that is equal to 8. If you were to check it on your calculator, it does check out. Okay. Let's do this second problem down here. I hope you can see that we're dealing with powers of 3. Both 27 and 81 are powers of 3 here. Okay. So we can turn 27 into a 3 cubed. 3 times 3 times 3, all raised to the 3x, and 81 is 3 to the 4th. We can multiply our powers together, and we get 3 to the 9x equals 3 to the 4th. And now we can realize, since bases are equivalent, we have exponents that are equivalent as well. So 9x equals 4, so x equals 4/9 would be our solution right there. The second strategy here is solving these guys graphically, and I'm going to show you a couple different strategies on Desmos, both of which are essentially equivalent, but I'm going to show you two different strategies. So for the first one, I'm going to show you how you can do this if you were to try to find x-intercepts. I focus on x-intercepts a lot when we're solving polynomials, so I want to try to make a connection here for that. So let's subtract 285 from both sides for this first one. So we have 15 to the 3x minus 285 equals 0. And we can think of this as then going to Desmos, and rather than typing in equals to 0, we can type in equals to y, and then look for x-intercepts. Okay? And those x-intercepts would be the values of x where y is 0. Okay? So let's go through that, and I'm going to just need to speak through it. I can't annotate my Desmos graph, so I'll just try to verbally talk you through it. Let's go there right now. So we have a y equals 15 raised to the 3x, and then we have a minus 285. And I think it's helpful to just look at the structure of the whole graph, make sure it is an exponential looking graph, and it is. It does show that exponential growth right there. But let's find our x-intercept. Our x-intercept is 0.696. So that's the value of x where y is 0. And so x is equal to 0.696. So that would be our solution right there. There's a slightly easier method on Desmos, and that's just graphing up, honestly, two separate equations as two separate y equals. So we could say this is equal to y, and then separately we could say this is equal to y. Okay, we're going to graph those two separate equations and look for where they intersect on Desmos. So I'll go there and do that right now. So our first one is y equals 5 raised to the 2x. And the second one, let's go back, what was it? 130. So y equals 130. And we're just going to look for where those two functions intersect. Zoom out a little bit, and we can see that they intersect at 1.51. And that would be our solution right there. X equals 1.51. Right, so a couple different strategies using some tech, using Desmos or any old graphing calculator, honestly, to help you solve for an exponential equation where the unknown is in the exponent. All right, and that's a good place to stop right there.